I'm going to solve question number 2, that is regarding transition metal complexes. May June 2023, question paper 4-2. Question number 2, A part. Say two typical chemical properties of transition elements. Number 1, they make colored compound. Number 2, the second property is they make complexes. They make complexes or complex ions. B part, an aqueous solution of the cobalt 2 salt contains complex ion, this one, hexa aqua cobalt 2 positive. Define what is a complex ion for 1 mark. And here is a definition basically. Molecular ion that is formed by the dative bond of ligand with the metal ion. Ion, as it is asking about ion formed by the dative bonds between metal ion and ligands. So that type of ion is called complex ion. Next one, part 2, hexa aqua cobalt 2 sample are reacted separately with excess of aqueous ammonia with exchange of concentrated HCl and with excess aqueous sodium hydroxide as shown in figure 2.1. This is the actual complex, and that is pink in color. And addition of NaOH is going to make C. Addition of excess concentrated HCl is going to make B. Addition of excess aqueous ammonia is going to make A. Complete the table about the reaction shown by this complex. Number 1, excess ammonia A. Here are 6 H2O, 6 ligands, 6 water ligands are present, so they will be replaced. Cobalt, small bracket, NH3, that is also 6 over here, and 2 positive. Color and state of the cobalt species formed. This is a new species that has been formed, and basically its color is brown solution or yellow brown solution. It's a water soluble because it is having a positive charge, and its color is brown solution. You will have to memorize these color. What is the type of reaction? The type of reaction is H2O has been substituted by Na3, so it is called ligand exchange reaction. Ligand exchange reaction. Come to the second one, an excess of concentrated HCl. If HCl is going to be introduced into this solution, and that is excess HCl, and that is, that is the highly soluble component in water. So what will be the new complex? CO, and here will be Cl4. There is no need to draw this small bracket because there is only one element or one type of element, and square bracket close. Overall charge will be equal to 2 minus, because cobalt is equal to 2 positive here. Same is the case over here. In this case, water is a neutral ligand. I'm going to write over here. There is no charge on the H2O molecule. So to make sum on the complex 2 positive, that is because of cobalt 2 positive. So charge on this complex is because of the charge on the cobalt. So this is the complex, and what will be its color? Its color will be blue. Again, it's a water soluble because it is an ion and blue solution. Next one, what is happening once again? H2O has been replaced by Cl negative ion. So again, it's a ligand exchange. Come toward the last row. When there is addition of excess NaOH, number 1, if I'm going to add excess NaOH, then only two OH have been introduced. I mean, precipitates are formed, and here is the basic theme or basic formula. I mean, there is NaOH is acting as a base over here, and first, I mean, it's going to remove two hydrogen, leaving behind two OH group inside this coordination sphere. So cobalt and two water molecule has lost its OH is H, sorry, H positive ion, the remaining is OH, and they are two in number. Remaining water molecule will be equal to 4. So overall, there is no charge. There is zero charge, or there is no charge. And so that's why it's a solid. I mean, it's a precipitate, and its color is blue precipitate. Sometimes it is also written as pink precipitate. So generally, you can write a pink precipitate, and the type of reaction. Initially, this is an acid-base reaction, but finally, as you have seen that a solid has been formed, so we will write precipitation reaction. Precipitation reaction is the final type of this one. Part C, ethane diuretine C2O42 negative ion can act as a bidentate ligand. Explain what is meant by the bidentate ligand for 2 marks. Bidentate, bi mean to, dentate mean it can make dative bond ligand. First of all, what is a ligand? Ligand is a molecule, is a species, a molecule, a molecule having two donor atoms and each donor atom has lone pair, a lone pair. Number one. Number two, what is the next property? And they can donate the lone pair of electron to the metal ion. And it can make dative bond with metal ion by donation of lone pair. Donation of lone pair. Next question, that is the most important question, in my opinion, that is about stereoisomerism. The complex that is cobalt, diaqua, and that is oxalate ion, bromo, chloro, negative. So this whole complex exists as a stereoisomers. Complete three-dimensional structures are diagrams in figure 2.2 to show four stereoisomers of this complex. One thing that is over here that he has fixed this ligand, that is oxalate ion ligand, and it's in all these four diagram, it's having the fixed structure. First of all, I'm going to see its coordination number. So coordination number is equal to 6. Two ligands, it's a bidentate ligands, 1 into 2, and it's a monodentate ligand, it's a monodentate, 1, 1. So overall, I mean 2 plus 2 plus 1 plus 1, total 6 bonds are, dative bonds are there, so its coordination number is 6. So its geometry is, as it is shown over here as well, it's octahedral. Octahedral geometry is over here. Then we know that in octahedral geometry, there is a possibility of cis-trans isomers, and there is also the possibility of optical isomers. In my opinion, first of all, we will make, and you should make, cis-trans isomer. Then we can convert the cis isomer into optical isomer in most of the cases. In most of the cases, cis isomers is having optical isomerism, but trans is not having optical isomerism. Now, how to draw the cis-trans isomer first? In cis-trans isomer, number one, I'm going to check if there is a possibility of all cis isomers, I mean all cis with respect to all ligand. Cis with respect to all ligand. Cis with respect to all ligand. And the second one, if it is possible, trans with respect to all ligand, but that is not possible in bidentate case if the only if the one or the more than one bidentate ligands are there, so not possible in bidentate ligands. So it may not be possible in this case, in these four options. Then the next thing is, first of all, make says, all says, trans with all monodentate or the bidentate ligands. And third one is to make uh, ton by ton different ligand says with respect to one pair, if the pairs, different pairs are given, and trans with respect to other pair, and then you will convert cis into optical isomer and so on. Now come toward this one. First of all, you can see that there are two water molecules and two halogens. One is Br and another one is Cl. So first of all, I'm going to make cis with respect to all ligand. It's already cis. This bidentate ligand is making cis structure. So let's suppose I'm going to write H2O over here, H2O over here. Same is the case H2O over here. So this complex is cis with respect to H2O. Let's suppose Cl over here and Br over here. So it's also cis with respect to halogen. Now I'm going to make trans isomer with respect to the other one ligands. So in this case, I can make H2O over here and H2O over here. I cannot make trans with respect to all because there is a bidentate ligand, as I told you. In case of bidentate ligands, it's not possible. So let's suppose Cl over here and Br over here. This is cis with respect to water and with respect to halogen. This is trans with respect to water, but yet cis with respect to halogen. Now I am going to make trans with respect to halogen and cis with respect to water. So these are very simple. These three are quite simple, very simple. This is all cis, and this is a trans with respect to H2O, and this one is a trans with respect to Cl and Br, halogens. Now the fourth one, what should be this one? I'm going to make an optical isomer of this cis. Because cis structure, especially whenever there are the monodentate ligands, then cis structure has its optical activity or optical isomerism. So I'm going to make its optical isomer, how it will look like when it is placed in front of the mirror. So let me draw it first of all over here, and here it will be, H2O, and it will look like Cl and oxygen, and here is again oxygen. Over here it is H2O, and here it's Br. Another way, and that is the easiest way, you can swap these two groups. One is at dark wedge and other one is lying at the normal line. So I'm going to write Br over here, Cl over here, H2O and H2O. So these two, it also says with respect to all, but these two are, you can say, enantiomers. These two are the optical isomers of each other. So in this way, that there is an easy way to draw the structure, to draw optical isomer of 3D structure of octahedral complexes. See it in other way around. This oxygen that is on dashed line, here it is in front of Br, And here this oxygen was in front of Cl. So these two are having different optical activity or optical nature. Come to the next one, state oxidation state of the cobalt in this complex and state the isomerism as shown. So as I have told you, we can find the oxidation state by checking the different nature of the ligands. So in this case, water is basically in this complex. I'm going to write it over here. In this complex, water is a neutral ligand. C2O4 is a negative ligand and it is bidentate ligand basically. It's having two negative charge. So it is having two negative charge. Br is a monodentate but one negative charge ligand, I mean anionic ligand. Cl is also equal to anionic ligand. So must be so sum must be equal to 1 minus. It means that this cobalt should be having 3 plus, so that the sum of these number will be equal to 1 minus. If I'm putting 3 plus over here, then sum of these number will be equal to 1 minus. So it means that its answer is plus 3. Type of stereoisomerism, as I have told you, that there is a possibility of cis-trans isomerism, and the one I draw over here, in my opinion, that was optical isomerism, and so on. That's all about this question. Thank you.